We've got two different Gelsight systems here that we're going to be sort of running through today. And the main premise of what we're trying to give you an overview of is some of the new features in the software and the sort of capability of the system itself. So we've pre-recorded a couple of the functions. So I think there's 5 of them we're going to run through. They're sort of 2-minute snippets that roll for about a 10-minute period. Then after that, what I'm going to do is run through a live demonstration of the Gelsight Max, which is the higher resolution system of the two. And then we've got a sort of open forum or a bit of time for any questions that anyone has. So we've muted everyone within the chat. So if you've got any questions, just please type them into the sort of chat box on the side of Teams, and we'll sort of work our way through them at the end of the presentation. So please don't be shy, fire away. We've got enough time to run through questions, complicated or not. Let's make sure that everyone's got a nice overview of the system and the principles of why people are using it. Okay. So yeah, once again, thanks everyone for joining us, and we'll sort of start running the film that we've got, and then we'll pop back later on with some more information. So here we have the Gelsight Mobile Series 2 system. So the Gelsight is used to characterize surfaces. So whether that be a surface defect, surface roughness, a radius, a chamfer, a break edge, hole diameter, the system is used to characterize those kinds of features and give us a report or a template to report to capture that information so that we've got traceable data to suit the current industry standards within aerospace, automotive, and high precision machining. So the system itself is a 5-megapixel camera. We've got a lens and then a ring set of LEDs. So as an example, when I place my finger over to the end of the sensor, we can see that we get an instant surface depiction. By clicking the black button on the sensor, we can see that each individual LED position lights, and we effectively take a photo. So using an algorithm called photometric stereo, we stitch those images together to create an STL file. And that STL file is what we use to create those surface characterizations. So whether that be the roughness, our pitting, depth of mark, but we use that data set to capture that information to create a report to understand what's happening on that surface. So within the latest version of the Gelsight software, we've got something called defect detection. So effectively, the way that this works is we can define a boundary within the field of view of the pad. And if we place a defect into that area, it will automatically detect it. We'll characterize the length, the width, the depth, and the volume automatically. The main benefit to this change is that we can run the routine automatically within the software. So if I place the pad against the surface and click the button, it'll automatically do all the information for me. I don't have to draw any boundaries or anything like that. So what I'm going to do is in the software, I'm going to click Run Routine, and I've got a 50 micron tolerance limit for my effective zone 1. So on my component, I'm going to go and take a scan, place the defect into the field of view, and click Capture. So that's effectively all I need the Gelsight for. I've taken my capture, and now the system is creating my STL file, and we're going to be able to do some analysis. So you can see in the top right corner, I've got Scan 02, which is the scan of the sample that I've just taken. You can see we've got a green box around it. That actually tells me that it's past the zone limit of 50 microns. So if I double click into here, you can see that we found the defect. We found all of the other little defects on the sample, which are these gray areas. And what it's done is it's automatically profiled the sample in the worst case area. So you can see here in the top right, I've got my length of 6.433 millimeters. I've got a 0.762 millimeter width, area, volume, and depth. So now as an operator or a user, I would just need to go to the PDF button, and there's a report of all of that information. So I can save that onto a network or export it, print it out, stick it to a tracker sheet for the defective part. But it's a really good example of how I've gone from there's a defect on my sample within a specific area that I need to tolerate or understand. Within 3 clicks, I've got a report of a traceable set of information that we can use to understand a little bit more about that. You can use the Gelsight system to measure radii. So what I'm going to do, nice and quick, is take the system to the end of this larger part, place it against the surface, and we can see the radius. Click Capture. So whilst that's analysing the data and creating that STL file, we're starting to see a lot of our customers that manufacture larger samples. So this is an example of one that they're struggling with having to take the sample to a inspection machine to be able to measure things like radiuses, break edges, chamfers, fillet reliefs, that kind of thing. So the idea behind using the Gelsight system is we can bring the system to the part as opposed to the part to a measurement system. One of the benefits to that being that if I manufacture a 3-meter long part and it's wrong, I don't want to have to put that back into my machine tool to rerun or blend out any of the radiuses that potentially could be wrong. So the idea behind the radius function is, in the bottom left here, I've clicked my radius, I draw a profile along the radius, and you can see the system snaps the blue boundary to that radius to output us a result. What we can also do is if we go to the pencil, we can add in a number of radiuses. So if we said 11, and then I went to do that over a 0.5 millimeter area, and we click Analyze. Now what this has done is we're looking at the change of radius. So over a 0.5 millimeter area, we're looking at each individual radius, and we're outputting the worst case, or the minimum, the maximum, and the median radius. So that gives us an understanding as to whether potentially the tool's wearing, or there's a drift in the machine that's actually cutting the radius itself. Using the Gelsight Mobile Series 2, we're able to capture profile roughness and surface roughness. So the capability of this equipment is to measure between 2 and 20 RA, but using the Gelsight Max system, we can characterize between 0.2 and 20 RA. So just something to note. So in the bottom left-hand side of the software, I can go to Run Routine, and I'm going to select my 10 micron SA measurement. So now the same principle again as our defect detection. I can place the system over a sample. So this is a 3D printed texture. I can click Capture. We're going to characterize the surface roughness, or the SA value, within that boundary. So the system can characterize other surface parameters, but the main one that we're currently seeing customers use is surface average. So you can see here we've got a plot of the surface roughness. I've got a pass because it's below my 10 micron limit, and you can see the other parameters that we're currently exporting with some blurb and information as to how that's been characterized. So when we're now looking at profile roughness, what we can do is go to my profile roughness tool, and in the same principle, I'm going to draw a profile across the sample, like so. And we can now see we've got our profile roughness. So in a similar fashion to the radius, we can do a number count. So let's say we're going to do 15 over a 1 millimeter spacing. And I'm going to click Analyze. So we've now got 15 profiles, and we're outputting the average RA as well as just the specific RA for that individual profile. So if I wanted to report these, both of these measurements, I can go to my PDF and save. So as a first instance, we've got our SA and the other surface characterizations. We've got our movable PDF, so I can set that to that position. If we scroll to the second page, we've got our movable heat map again, as well as like showing where I've taken my plot for the profile roughness. So it's a very quick overview, but as a principle, it shows how we can characterize surface roughness as well as profile roughness using the Gelsight Mobile Series. We can use the Gelsight system for dimensional checks. So on the example I'm going to run through here, we've got a hole diameter as well as the angle and the length of a chamfer. So I'm going to bring the Gelsight system to the hole diameter to start with. I'm going to place it over, and I'm going to take a capture. I'm then also going to take a capture of the chamfer. You can see nice and clear there. So if we were to look at the hole diameter first, go into the software and I can click hole diameter. I can draw the boundary of where the diameter is, and the software will find the edge, and it gives me the diameter as well as the circularity. So we can look at reporting this. So if I was to go to the PDF function and click save, we've exported a report of the information related to that diameter. So now what we're going to do is jump back into our Scan 06, which is our chamfer measurement. We can see here we've got the chamfer. So what I'm going to do is I'm going to go to the drop down, and I'm going to click on profile geometry. So what I can do here is I'm going to draw a profile that just surpasses the edge of the chamfer, and we can see here that we've got the shape. So the blue boundary is the area that I'm using to review the chamfer. What I also need to do is to level the left-hand side, which is subsequently the flat edge that I'm assuming the angle from. So the chamfer starts at the area where my blue boundary is here. and it finishes where the drop-off point is in this direction here. And we can see that the chamfer, which is the x1 to x2 distance, which is the blue point here to the red point in this axis, is 1.287 millimeters. We've also got an angle of 37.62. So if I was to go to the PDF function now and report this, we can see that we have the chamfer. We've got the information related to it. We've got the heat map, as well as the profile and the information down the left-hand side here. Using the Gelsight system, we're able to quantify the size and number of particles within a field of view. So what we've got down on the left-hand side is some coffee grounds as an example for what we could use as particles or explain the particle function. So I'm going to take the Gelsight system, I'm going to place it over a section of the particles, and I'm going to click capture. So within the software, we're creating our STL file at the minute. So the system is currently taking all of those images that we've taken and creating that point cloud. So now I'm going to load scan number 7. Click OK. So in the bottom left, I've got my particle detection. I'm going to click particle detection. That is automatically going to run the routine to find those individual particles that we see on the surface. So you can see each individual one has been color mapped. And on the side here, we've got the size of those being reported. So we can see every one of those individual particles, where they are, the area, the centroid and the X and Y orientation, and it gives us a lot of information on that specific surface. So for me to report that, I can go to my PDF button, generate the report, and I'd like to save those changes. And you can see that we've got the heat map of the surface. We've got the actual particles themselves, so we can review some of the specifics. And then we've got the number of particles, percentage covered, minimum, maximum, and the max particle amplitude. So, there we go, you can hear me again now. So a lot of information we just went through, so I appreciate, I can see there's been quite a few questions. So what we're going to do is just run through a live measurement using the Gelsight Max. So we're going to look at a roughness standard, and then in one of the questions that we had, I'm going to be able to answer the question as we go through on the second measurement that we do on the Gelsight Max. Okay, so the Gelsight Max in comparison to the Gelsight Mobile Series 2, we've now got a 16 megapixel camera, so you can see it's a slightly taller system. Effectively, we've got a smaller field of view, but that 16 megapixel camera offers us a lot more point data. So we're getting a higher resolution, and the quoted Z accuracy of this handheld system is 0.3 of a micron. So we're achieving some incredible accuracy on something that we can walk around the shop floor with. So the first measurement that I'm going to run through is our roughness. So I've got a roughness standard here in my hand from one of our contour machines. So I'm going to take the system, and I'm going to just take a scan on this roughness sample. So bring it over to it, and we can see the texture of our standard. So I'm just going to click capture, and that is everything I need to do on the roughness measurement. So we did a brief run through of the roughness measurement within the video, and we've obviously got on the Gelsight Mobile Series 2, which is this system here. We've got a 2 RA to 20 RA or 2 SA to 20 SA capability, whereas on the Gelsight Max we're able to measure to 0.2 to 20 RA and SA. So I'm going to go into the scan now, so scan 01, what we've just taken, and we can see the texture and the actual roughness of our artifact. So what I'm going to do is go to our profile roughness, draw profile down, and you can see that we've got the roughness of that artifact. Okay, so if I go to my PDF and report, I've been able to measure the roughness on a handheld system, well, within about 30 seconds. Okay, so that's one of the main benefits of using a Gelsight Max. We've got a high resolution set of data, and we're able to achieve a little bit more capability in the lower value of measurements that we take. So going to one of the questions related to access and what's the, if you had a convex shape, what would you be able to use the system for? So it's a slightly subjective question because it depends which system. So what we have to do is calculate the effective radius that the system can reach. Sometimes there might be a feature or a defect or an element of the surface that you're trying to depict that the sensor can't access. And what we use replica material. So this set here I've taken before we started. I took a replica of the internal, and I'll bring it to the camera so you can see it, the internal of this bore here. So what we can do is within the software, if I go back to my capture area, and I now take this replica, I take a measurement on the radius, we can see there's some defects. So I'm going to click capture. And I've now taken a data set of an area that I can't actually physically get my sensor to. I'll be able to look at the radiuses, I'll be able to look at the break edge, I'll be able to look at any of the defects that are there. The idea being that it sort of opens up the capability of what we can use the system for. Now, using the replica material, we do induce some inaccuracies. So the replica that I've just used has got a quoted accuracy of a micron. So we have to take that into consideration when we're looking at speccing out which system we would use for specific customers. So we can see here we've got this step change within our radius, which is the main area they're looking at. This has been, we sort of added this defect into the surface, so it's deliberately there. So what we're going to do is we can look at our radius, and I can draw my radius across in this direction, so following along the edge that we see, and we're able to depict the area as to where our radius is, which is this here. So we're still able to measure internal radiuses or external radiuses that we can't access with the system on features like this. Again, if we were to look at the 3D data, so we can see the 3D data here, this is obviously effectively the wrong way round. So our actual part is is a diameter or a bore, so we don't want it to be positive. So what we can do is we can go to our replica function, we can click yes, and what that does is it actually, within the point cloud that we see, it flips the data. So if previously we had a part that was like this and we replicate it, we can now flip it to be true to the actual components type. It's one of those functions that people, when you're looking at operators or some of the less skilled people that are going to be using the system, they need to understand the differences between whether it's a positive or negative in relation to the tolerance of the part. So if we now go back to our analysis area, you can see that the radius has flipped direction. So we would just need to revalidate the area that, or the position that we've taken the measurement. And you can see that we're still able to measure. Okay, so that's the idea behind showing you the replica material, as well as the Gelsight Max and the use cases for the Gelsight Max with things like roughness and higher accuracy step changes. Okay, so on the right hand side of me here, I'm not looking away. I've got the questions all pulled up on the team, so I'm just going to read them out so that everyone knows which one I'm working on. So what is the field of view, and can composite images be made? So the field of view on the Gelsight Series 2 is 16 millimeters by 14 millimeters. And on the Gelsight Max, it's 15.5 millimeters by 8.8 millimeters. So that's the field of view that we can see. So obviously you can see on the Gelsight Max that we're slightly more rectangular shaped. With regards to looking at composite or stitching, I'm presuming that's hopefully what you mean. So the system is normalized to itself. So when we're looking at data sets, we're effectively measuring something in reference to another surface. So one of the benefits from that is that I can walk around with this in space, and it doesn't matter whether I take a point here, I take a point here, or a point here. The difficulty we have when you look at stitching is that I don't know where I am, so how do I stitch the data together? So unfortunately, on specific measurements, we can't do it. However, there's some customers that we have that will use the STL files. So if I was to jump into a scan, go to the 3D data, they export the STL file, and they'll manually match it themselves. So if you were looking to do stress analysis and there was 10 areas on a component, they'll take 10 separate scans and they'll fit it to the specific position. They'll run it through its trials to see whether that's going to cause a failure point or a fracture point on the component. So there's sort of workarounds for it, but specifically I can't take a data set and merge it and create a larger depth map. Okay, hopefully that answers that one. So I'll go down to the next question, which is, can it read highly reflective surfaces? Are there any limits to the access of a concave radii? So hopefully we sort of went through some of the principles to access issues. And if you've got any further questions or queries on that, then please let us know. If we refer to the top section, so when we look at the sensor itself, and I've got some samples here that will be good to demonstrate that. So the way that the pads work is we've got a coating on the end of the pad. So if I take the lid of the system off, and hopefully you can see it okay. So I've taken the gel pad off, and we can see effectively our optical system here. The pad itself has a coating. So we can see on one side it's got the coating and the other side it's clear. So effectively what we're doing is we're reviewing the deformation of the pad on the reverse side, which is why when we take a sample, so whether that be a matte black sample, so I've got a matte black block here, which is an additive block. So if I place that onto the system, we can see the texture. But now if I was to take my shiny aluminium component, which I'll bring it to the camera so you can see it. So a shiny aluminium component, which has got a nice step across the surface. You still see the texture. So with regards to the system, the main benefit, or one of the main use cases for the system compared to non-contact systems, is that we don't have any issue when we're looking at a reflective surface, a transparent surface, or a matte or discolored surface. It makes no difference to us. We're purely looking at the texture, which is quite helpful, especially in some of the aerospace and high precision industries. So going on to the next question, does the handheld device come in different sizes or is it standard sizes? So to answer that, unfortunately at the minute, Gelsight only provide a system, or the two systems we have here with the field of view. The reason for this is the difficulty we have is that if you were to take the Gelsight Series 2 and we were to say I want a pad that's 3 or 4 times the size, unfortunately, for the way that optics work, the camera starts to get further and further away. So what we don't want to do is bring in a sensor that's this tall to come and measure a part, because it proves to be slightly less portable and handheld. So at the minute, we've currently got the two setups and field of views of the two systems. But again, it's always good to understand specific applications, because we might be able to communicate with Gelsight to understand if there's potential of some other systems or sensors. Okay. So the maximum area that the Gelsight can measure. So if we were to look at the Gelsight Series 2, because it's technically got the largest field of view, that is your 16 millimeters by 14.5 or 50 millimeters sort of zone. So that's if we jump to the software, sorry. On the Series Gelsight Max, you can see that it's a rectangle. And on the Gelsight Series 2, we've got a larger step in the height of the scan. Okay. So the next one I was moving down to is how long do the Gelsight pads last for? It's a slightly subjective answer. It sort of depends what you're doing. So the pads themselves, if you were to be measuring samples like this one here, so we were looking at sort of step height changes and radiuses and potentially the roughness of these samples, I'd be looking to try and get our customers to measure maybe 200 scans per pad. If we were to be looking at break edges, or we were looking at debris that was left on components, we might be looking at between 100 to 175 scans. I've seen customers that have used pads that have done 400 scans and they're still calibrating really well and they're not having any issues. So it sort of comes back to the analogy of we've got a piece of equipment, although it's handheld, we're trying to chase single-digit micron measurement accuracies, so we need to look after it as best we can. So if we can clean the surface before we measure it to remove any oil or grease or loose debris that's on the component, and then if we can look after the pad, place the lid onto it after we've used it, and also run through the cleaning process. So every sort of 50 scans, or when we see visual debris on the pads, we run through a cleaning process using some alcohol wipes on there. So it's slightly subjective, but I'd say as a minimum, we'd be looking at 100 upwards to sort of 400 scans. Okay. How easy is it to compare STL files to see differences? So if we were to take an STL file out, it's not something that we do within the Gelsight software. So we at Sempra here, we work with Polyworks. We use a lot of Polyworks, and on some of our other systems, we're able to do CAD compares. So what we do is we take our CAD for the sample, we'll take our STL file, we'll merge them together, and then you can run through and do your heat map analysis to the CAD as opposed to it being to its normalized, or to itself, I should say. It's not particularly difficult, if I'm honest, the stitching of those two together, and I'm happy to run through it. It probably wouldn't be today, but I'm happy to run through the principle of how it works. To export the STL file, which is an element of it, is within the software. If we were to go to one of our scans, so if you look at our roughness, I can literally just click that export STL, and that's the export for me. Okay. Hopefully that answers it. Might not have done, but yeah, fire away if you need to. What's the smallest radii it can measure? The honest answer is I haven't tested it to a limit of going below a 0.1 for access reasons. I think on the Gelsight Max, we've got a field of view of about 250 microns. So providing that you're happy with the resolution of the system in Z, which is obviously pretty incredible for a handheld unit of 0.3 of a micron, in theory, we should be able to measure down to sort of 50, 25 microns and get a reading. The difficulty when you look at radiuses, and if you're to refer to sort of CMM world and ISO standards, etc., we need to try and measure 120% of the 120 degrees minimum, of the radius to depict an accurate measurement. So a lot of the radiuses that we see on components, we're only got 40, maybe 50 degrees worth of area to measure. So there needs to be a consideration as to the repeatability of that measurement. And that's not just on a Gelsight, that's unfortunately on any measurement system that's used. So yeah, we can go down to effectively to the resolution. So we probably need maybe 10 points to construct our radius. So yeah, say sort of 25 micron size, I think we'd be able to achieve. Okay. You measure roughness parameters be outputted to Python? Yes. So within the scan data, so I've seen quite a few people that within the software they output a TXT of the profile that we see. So as an example, I'll just show you the data set. So if we were to look into here, I've got my roughness measurement that we've taken. So what we can do is we can save that to a file, and effectively we get a TXT of the profile. So from that data, we're able to run it through Python, do any of the other measurement that you might require or specific measurements that you might require. And what I've also seen some customers do is they take the profile data out themselves and they'll create their own routines for specific roughness parameters that might not be to standard, but are specific to their needs or their parts. So yes, it's not really too much of a problem for us. We just click that save to file and you get a TXT of every one of those points. So yeah, not too much of a problem for us. Does dust stick to the pad? So running through, so does dust stick to the pad, for example? Is it static, etc.? So we don't tend to see issues with it being static. You do sometimes get residue stick to the pad. So within the pad cleaning process, what we're trying to do is to remove any debris that's left onto the surface. You could see on my Gelsight Max one here, if we go to the software, you can see that I've got a small piece of debris that's been induced into the measurement. So what we do is we'd avoid that because I know it's on the pad because it's been, you can tell by the shape of it. So we'd avoid that for the measurement. We run through a cleaning cycle. And in theory, the next time I go to measure, we wouldn't have that debris that's on the component. It doesn't help that my fingerprints have been all over the parts, and especially residue off of your fingerprints. You can actually pick up the sort of the step heights because you'd be amazed how thick and how oily some people's fingers are. So you see it on the components that we've got. Okay. And the last one, what is the maximum range in the Z-axis? So it depends on, again, it's a slightly subjective answer. So it depends which system you're using. So the focus range on a Gelsight Max is 250 microns. So that's sort of the limitation as to the size of depth that we'd be trying to measure. On the Gelsight Series 2, we have about 2.5 millimeters of pad depth. Now, the limitation when you look at Z depth is it's effectively a short equation that you work out. So if you imagine I had a surface that's like my hand and I had my finger and I prodded a hole into my hand that was at the diameter of my finger. Now the pad, because the width of the mark, so the width of our mark on my hand is about this wide and it's about this deep, the pad is effectively going to roll into the bottom. So we won't see the bottom of the surface. So it's depending, we try to aim for a 1-to-1, so the scale of being the mark being 1-to-1 as a minimum of depth to width. So I can show an example of that and how easy it is to understand when you've not hit the bottom of a mark. We jump to the software. So I've got a component here that's got effectively a through hole, but the aim is to try and show you the principle of how, as an operator, you can understand when you've not hit the bottom of a component. So you can see here my through hole. So we've got it's amazing the texture you pick up with this Gelsight Max. But the through hole area and the area where I've not taken a scan, you can see that it stays this sort of matte grey colour. And the matte grey colour insinuates that we're not touching a surface. So whether I look at a transparent surface, so if I was to look at the screen of my phone, even though it's transparent, we'll still see a texture change. So we still see the texture, okay? So we can tell the difference between when we're against the surface and when we're not. And that sort of tries to help understand the maximum ability for Z heights. It's a slightly subjective answer, I know, but when you use the system and we go through the training, we train the operators to understand when they're at the bottom of a defect or whether they're at the sort of they're okay to take the scan. Okay, and I think as far as that goes, I've rattled through those questions as I always do, but I think it sort of run through the principle of everyone. So is there any more questions that people have or anything specific anyone wants me to run through whilst I'm here with both systems? I'll give it 30 seconds or so. You mentioned calibration. What's involved? Okay, that's a good question. So to my right here, we have our calibration artifacts. So effectively, the way that we calibrate the system is we take a scan on what's called our optical flat. So you can see, hopefully, we've got our optical flat. So the idea behind the calibration routine is I will take my sensor. We've got an aligner for the calibration. I take the probe, and we take a scan like this on our optical flat. Once we've completed that scan, we go to what's called our BGA. So our BGA is an assortment of spheres, effectively, in a specific position. And to give you an indication, it's quite small, but hopefully you can see the setup of the balls. So the idea being, we take a scan at 0 degrees, we rotate, take another one at 90, 180, 270. So that's 5 scans so far to get the calibration. And the last one is something that we call this is a G500 plate. So we've got a known groove depth. So the depth here, so you can see there's a flat bottom slot. So within the software, we input a value, which comes from our calibration certificate for the system. So the inputted value comes with a sheet, and there's a number down here that we would input into the software. So when we calibrate, we take that final scan on our G500, which is effectively the same as the other ones. So we take our sensor and take a scan. What that's doing is we measure the depth of that flat bottom slot, and we output a deviation to the known number. So within my software, so if we go to the software, I've got my calibration artifacts. So if we were to look here, I've got the known value for the certificate I've just shown you. And effectively, I don't allow more than a 2% deviation from that artifact. So that's how we control the accuracy of the system to ensure that we're going to achieve the required measurements. Okay. Hopefully that answers that one okay. Are you able to send an example STL file to me so I can look at the software, etc., and have a play with it? Yeah, that's fine. That's not a problem at all. If there's anything specific or a specific sample type that you'd like, so whether that be a roughness standard, whether that be a radius, etc., then let us know, and I can take the scan and send you the STL file. That's absolutely fine. I can also do it on the Gelsight Series 2 as well as the Max, so you can see the deviation or the changes within the resolution of the system. Are the calibrations artifacts supplied with the system, or do you need to carry this out? No. So when you buy a system, again, I'm going to go to my box on the right-hand side here. So the idea behind the Gelsight system is that we're fully portable. So we have a Pelly case. So within the case, we've got areas to hold spare pads. We've got the areas where my calibration artifacts just were, which are in here. We've got the cleaning kit area. And the last element is, if we take the first case off, is that we have our tablet to run the system. So although I've got my system currently behind me running on a laptop, we normally supply to most of our customers a tablet. The principle being, we've got a keyboard, a detachable keyboard. So I can take that off for the example, place that on the floor, as not quite a place, but so I've got a tablet here. I could place or attach the Gelsight unit, and I could have both of them running. I've obviously not got the cable on my Series 2, but we can go and do our analysis, and this is all touchscreen based. So all of those profiles that I've been doing with my mouse, we can do with it on the touchscreen. So deciding the area, the field of view, etc., we can do that on our tablet. So everything comes within the kit, and it's a key part to the system. So that once we've done our scans and we've completed our measurement, I can pack all of the equipment back up into my box, either chuck it back in the calibration area, or I can go to the next cell or the next department to go and have a look at some samples. So everything that you would need related to calibration, pads, cleaning, laptop is all kept within this little Pelly case. All right. So any more? Do you support training on the system? Yes, again, so unfortunately for training, it will probably be myself who would be doing it. So whether as you see that as being a positive or a negative, I'll leave that to you. But yeah, the key thing with these systems is implementation, and it's a key thing that Sempra try to work on. So it's very easy for us to sit here and sell equipment and say to people, right, go and off you go and sort of go and use it yourself and figure out how to do it. But it's the main value that you see from using equipment is how it's implemented and the understanding of it. So our analogies within the business is that the return on investment is related to 80% of the implementation and 20% on the system capability. So the way that I normally run through the training sessions is that we do a half day on site or here, whatever suits. We try and look at samples that you've got so that you've got an understanding of how the best practice to measure those. And then a month or two later, we come back in for another half day and we go through any of the queries or questions that you might have to sort of just try and steer you on your way, really, to make sure that everyone understands the system. So it's a full day's training, but we split it out to give you the best use of it. And again, I mean, with a lot of our clients that currently use the system, we run like a quarterly catch up. So we just jump on a Teams call for half an hour just to make sure that everyone's happy and using the systems, because we tend to find that when people go and they acquire a Gelsight, it just rolls on to them using the system more and more because they save so much time by using the system compared to other sort of traditional methods, we should say. Force effects. So I've actually run through some studies on the measurement force. To a point, there will be a force applied, but if I was to go to the software to answer the question, it's the best way to do it. So we need to make sure that we've got full coverage of the part. So the force will affect the measurement to a point. So if I was to go back to my roughness standard and I was to place the gel over the standard, I'm just going to remove some of the hair that we had. So if I was to not apply too much pressure, again, so not effectively creating a correct measurement, we can see that I've got this almost bubble to the side where the pad hasn't contacted. If I was to apply more force to bring the system into focus, we've now got the surface that we need. If I apply more pressure, because the part is stationary, the surface isn't changing more. So we're not seeing a change to that surface. Now, if I was to apply too much pressure to the point where we were going to effectively rip the pad or break the pad, then that's another sort of element. But I don't tend to see a difference between the measurements, whether I was to apply a slight bit of pressure or I was to apply too much pressure. There's sort of a boundary. It's sort of that sine wave, really. The either side of it, the 10% either side, the measurement's been done incorrectly, but that middle boundary, we don't tend to see a deviation to the results that we see. Okay. Can product-specific routines be set up on the system, e.g., identify scratch lengths per specific parts / areas, etc.? Yes, it can. So luckily, I've got a routine set up for this, which shows it quite well. So I'll quickly go into the principle of how this is done and the way that they're built. So if we were to look at our one of the routines that we were in on the video, so I've got a surface average measurement that's being taken at a 10 micron limit. So what I could do for, say we've got a zoned part, so some companies have a zone 1 can have a 5 micron limit, zone 2's got a 10 micron, zone 3 50 microns. So what I could do is I could go to my 10 micron limit and I'm going to click new variant. And I'm just going to say this is my 5 micron limit. Say. So now we've got a new utility, which is my surface roughness at a 5 micron limit. And now I can go down to look at all of the parameters that I can output for my surface roughness. So if I was to change my maximum limit to 5 microns and automatically run the routine, that's brilliant. So now to set up the routine, I'm just going to go to a capture and define my boundaries for this specific sort of program, we'll call it. So now if we go to here, I've got my 5 micron limit SA, and it's already got the boundary from the 10 micron limit. Obviously on this component, it's slightly out, so I'm just going to unlock it, drag it to this surface here. Now I'm going to click Set as Defaults. And by setting as defaults, that now saves that specific position to where the roughness measurement is taken. So if we go to our capture window now, and I was to go to scan, run routine, and I was to click my 5 limit SA, you can see we've already had the field populated on the software. So if I was to take my sensor, go to the surface, click acquire, we've effectively within, I don't know how long that was, maybe 45 seconds to a minute, I've created a program, I've measured the sample, and I'm now, within the next sort of 5-10 seconds, depending on your processing power, I'm going to report the information for that. So you see on the right-hand side here, it's generating the 3D data. So on our Gelsight Max system, we're obviously taking a considerable amount more of points. So we tend to see that the processing time is slightly longer. On the Gelsight Series 2, I like to try and get the systems to work to about 5-second processing. So on the right-hand side here, you can see I've got a green boundary. So that green boundary is telling me that the routine is passed. So when I double click into there now, I've got a pass as my pass-fail criteria, which was the tolerance we inputted into the software. That is because my SA value is 2.62 as opposed to my 5 micron limit. So for specific measurement routines or measurement programs that you have, we can build you the routines, or we always train people to be able to do it anyway. So you just have a list of specific areas or zones or tolerance bands that you have for your specific parts. So hopefully that answers that question. I may have missed, but are you able to stitch 2 images together using a reference marker if the field of view needed is larger? So within the Gelsight software, you're unfortunately unable to stitch data together. However, if you had reference markers, you could do that within a post-processing software. So if you were to look at, say, Polyworks or GeoMagick as an example, we can then bring those 2 STLs together to look at full surface deviation. The reason that we can't do it within the Gelsight software is we don't know where we are to normalize. So it's probably something that I should go and speak to them about, because if we have a reference position, in theory we should or could stitch the data together. So I'll ask the question to Gelsight and see what comes back. So if you can make a note of that, I will get back into touch with you when I've got some information as to if they're looking at it or when it potentially could be done. Okay. I know you mentioned size of radius, etc., but what would be the smallest chamfer you can measure? So I think it's the same principle, and I know it's a terrible answer, but we've got a resolution on the system in an X and Y position on the Gelsight Max of, I think it's 2.8 microns to 3 microns. Don't hold me to the number, it's around that figure. So in theory, for the length measurement that you'd be looking at, we'd have the pixel spacing for that specific area. So within a measurement, you try and take maybe 5 consistent points within that field of view, depending on the requirement or the limit. So in theory, we should be able to see a 10, 15, 20 micron chamfer. It shouldn't really be a problem on the Gelsight Max system. I'd probably say upwards of 25 microns on the Gelsight Mobile Series 2. So it's just dependent on the specifics. If you've got anything in mind, then please get in touch, and I'd be happy to try it. It's the best thing to do. We've got some samples here, so if you've got a specific size in mind, I can look to scan it on the system that we've got here and see what happens, basically. Can you add pass-fail limits to routines? Yes. So hopefully we went through that in the program. Effectively, if I move this out of the way so that you can see it. So on our pass-fail routine, we've got at the top here. So you can see we've got our pass-fail criteria. If I was to go to the report and click PDF, within our report, it tells us that we've passed, as we've got our pass-fail criteria here. So within all of the routines, we can turn that off as well if needed, because some people just want to know the number, but they still want the system to run automatically. So yes, we can do both. It's not too much of a problem for us. Can you measure surface flatness? So the way that we would measure surface flatness is looking at the maximum deviation over the area. So we would have to define what's called a scratch function. And what we'd be looking at doing is taking the minimum and maximum points, which is effectively your flatness value. So to run you through the principle of that, it's not a specific flatness measurement, but it's a sort of workaround. So if we were to look at this sample here, what I can do is go to my scratch function. I can draw a closed shape. So this first closed shape is where I'll be looking to measure the flatness, and this second shape is where I'll be looking at the normalizing the surface to itself. So effectively now this is going to give us the high and low points on this surface. So you can see the minimum is in the center point, which is what I'd expect on a roughness standard, because they naturally sort of move. And then we've got the high point here, which is 21 microns tall. So in essence, there's 27 microns of deviation on that surface. If we were to look at roughness parameters, we can use roughness parameters to make assumptions to a surface as well. So if we were to define a boundary, say, over this roughness standard, we've got a routine called SZ. So SZ is the area peak to valley height. So there's some filtering applied within a roughness measurement, but in theory, an SZ value gives you the peak to trough, or peak to valley, as some people would call it, of the surface. So it's a workaround as it's being a specific flatness measurement, but in theory, it will give you the same output. Okay. So yeah, sort of, I suppose, is the answer to that one. All right. So again, lots of information. Everyone's got my details. So if anything comes up later on, please fire it across and we can try and get back to you with some more information. I'll give it 30 seconds or so, see if there's any more questions, because I can see as I was talking, they were firing in, which is always good, making sure that people understand what we're trying to do, which is brilliant. I think we might be okay. All right. So any other questions, as I say, please feel free to get in contact. Hopefully you all know about your ASMs. Oh, we've had one more. I knew that was going to happen. That's what I thought. Wait, can you give me an idea of system cot and replacement pad costs? Of course. So you might need a pen and paper because it's relatively specific. So if we were looking at the Gelsight Series 2 system, you'd be looking at a starting point of around 32,000 for the system. So that would be laptop, training, installation, the system itself, Peli case, so effectively the package. There's a little bit of variance in that, and depending on the system type that you go for. So they have higher X and Y resolution calibration artifact, which is a slightly higher cost, and that goes all the way up to sort of 40k ballpark, depending on the software level. So I'm happy, again, for the specific question, if you pop me over some details, I can give you some indication on the differences between softwares, because there's different costs associated to if you were to look at the Pro package, which is what I've been demonstrating here, and what they call the Core package, which is where you've got sort of the step height or offset changes and the scratch functionality. So you wouldn't have your defect detection or your roughnesses. Now, looking at the Gelsight Max, you're looking at about a 50k ballpark figure for the Gelsight Max system, and you can only use the Gelsight Max system on the Pro package of software. So the sort of price ranges are between, as a sort of ballpark figures, if you said between 32.5 up to sort of just under 50k. All right. But yes, if you've got any specific questions on pricing or want a package sort of quoted, then please get in touch with your sort of local ASM, as I'm hopefully sure you should know them already. Fingers crossed. All right. I think that's probably all the questions that we're going to have. All right. So, oh, one more, sorry. Oh, yes, of course, I missed the question. I was rambling on. So the pads themselves, so the pad cost is probably a sort of ballpark figures again. You'd be looking at about 125 quid up to about 150 quid. And the reason I say the difference is because it depends on how many you buy. So if you were to come and buy 30 pads, you'll get a slightly better rate per item as opposed to if you were to buy 4. Okay. So yeah, sort of a ballpark figure between sort of 125 and 150 pounds per pad. So when you look at the system, obviously there's the initial investment for the system. We try to look at the use case being that you may be spending between 50p and £1 per scan. But if you've got a 25 gram part that you save from the data you've got, then we're winning. All right. So that's sort of the analogy we use. So the package as well, when you buy a system, we generally supply it as a base unit with 4 pads. So if you need more or less, we can then decipher that, obviously, between ourselves when we're looking at supplying it. Okay. All right. I think I'm going to say it last time. Thank you very much for your time. I appreciate I've rambled on. So if you've got any questions that come up later, please don't hesitate to get into contact. Thanks for all for joining us. Yeah, it's been very nice to be able to go through what are some of my favourite bits of kit. Yeah, and hopefully we'll speak to you soon. Thanks very much.